Yo, welcome back. All right, we are going to talk about the quotient rule now. So, how do you take the derivative of a quotient? So, if you had f of x divided by g of x, so your quotient of two functions, turns out this is how you take derivative of it, right? So, we do know from past conversations, it's definitely not simply just take the derivative of each function individually and divide them, right? The derivative of a quotient is not the quotient of derivatives. It turns out that this is how you do it. All right, so the way I like to remember this is I like to think of the numerator as my top function and the denominator as my bottom function. So the way I remember this is bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. If you're doing derivative with respect to x of u over v, it's written, because some textbooks like to do that, vu prime minus uv prime over v squared. Again, it's the same thing, though. It's bottom times the derivative of the top minus top times the derivative of the bottom over the bottom squared. Remember, the product rule had a plus in it, product rule plus. Quotient rule actually has a negative in it. So now it seems like a bananas rule. Where does it come from? Well, just like any other derivative rule, right, we should know by now that it always comes from, yep, you guessed it, the definition of the derivative. So this very first line of work here is the definition of the derivative, right? So this is my function evaluated at x plus h, right? My function is a quotient, minus my function all over h as h goes to 0. And so what goes now on from here to here is a whole bunch of magical stuff. First, we get a common denominator. We add the fractions divided by h, like multiplying by a reciprocal. That'll get you there. Then remember this little trick. We did this in the product rule proof as well. We looked a little different, but it's the same idea in that we're really just adding 0 to the numerator. But we add 0 in this form. It allows us to do all these different separations and factoring and breaking up fractions over addition and subtraction and so on, so that we eventually get down to what we now know as the quotient rule. Bottom times the derivative of the top minus the top times the bottom of the bottom squared. All right, you might want to take a second and just to digest this and, maybe pause the video, screenshot that, rewrite it, and see if you can go line by line and make sense of all the work that I did here. If you can't, just ask me an extra help, no big deal. So let's just get right at it. So find dy dx when y is equal to. So here's the deal. I've said this before. A lot of times I'm going to ask you, hey, what do we have? So when you look at y, what do we have? And you would say, we have a quotient. So then I would say, how do you find the derivative of a quotient? What's the response? Use the quotient rule. So let's go get them. So here we go. The quotient rule says start in the bottom. You'll hear me say that a lot as well. So quotient rule, start in the bottom. So you have the bottom times the derivative of the top. Now, what is the top? The top is a sum. The difference. The derivative of a difference is the difference of derivatives. So the derivative of x squared minus 1 is going to be 2x minus 0. I'm just going to write 2x, right? So now we go minus the top, which is a binomial, so put it in parentheses, the top times the derivative of the bottom. Again, well, the bottom's the sum. The derivative of a sum is the sum of derivatives. So the derivative of x to the fourth plus 1 is going to be 4x cubed plus 0. But I'm just going to write 4x cubed. And then all over the bottom squared. Right? And that's us applying the quotient rule to take the derivative of this. Now, let's go ahead and spruce this thing up. Let's see what we get. So up top, I can distribute the 2x. So that's going to be 2x to the fifth plus 2x. Here, I want to think of this as, at least I would do this way. I would think of this as, let me distribute a negative 4x cubed, right? Because multiplication is commutative. So I really can put this 4x cubed right in front, and there's a negative in front of it. So I'm going to distribute a negative 4x cubed. So when I do that, I'm going to get negative 4x to the fifth plus, because negative times negative is positive, 4x cubed. Okay? And then all over the bottom squared, which please do not try and multiply that out. Leave that factored. So now hopefully something good happens, nothing crazy, but we do see we have like terms here. So those can go ahead and get combined. So we're going to get dy dx equals negative 2x to the fifth plus 4x cubed plus 2x all over x to the fourth plus 1 quantity squared. And there is your slope producing machine for the graph of y, or your instantaneous rate of producing machine for the graph of y. Now, a couple things here. I probably should look to factor the numerator in the event that maybe I can cancel some factors out. So you'll notice that, yeah, you definitely can pull out a greatest common factor of x, but even when I do that, what I'm left with is not going to be able to be factored into one of these factors, right? So because that's the case, and I'm not going to be able to simplify, I'm not going to do it, right? But you have to know how to do it, especially if it's a multiple choice, because you might have to find the choice that that is there. Obviously, you have to find the choice that is there. So you still don't have to do this factoring stuff, but in this case, I'm going to stop there. All right, let's go to example 2. All right, so it says find the equation of the line that is tangent to this graph at that point. So again, this is bread and butter stuff now, guys. Equation of a line, you automatically are thinking point slope formula. And what do you need to have in order to use the point slope formula? You guessed it. You need a point and a slope. Now, the great thing about this question is I actually gave you the whole point. Not only did I give you the x value, but I gave you the y value. A lot of the ones we've been doing so far, it'll be like at x equals 1. So then you'd have to plug 1 into here, e to the 1 over 1 plus 1 squared. That's e to the 1 over 2. That's e over 2, right? You'd have to do that. But in this time, we just gave it to you, right? Make your life a little easier. So now I got to get the slope. So now it's more than I have to get the slope, right? I want the slope of the tangent line, but specifically, right? We'll call it dy dx, specifically at x equals 1. Okay? So before I do that, I'm just going to get dy dx. So in other words, I'm going to get the slope producing machine first. So, all right, how do I do that? Well, I have a quotient. How do I take the derivative of a quotient? Use a quotient rule. So let's go get them. So you're going to have bottom times the derivative of the top. Well, what's the derivative of e to the x? Easiest one in America. It's e to the x, right? Then minus the top times the derivative of the bottom. Well, what's the derivative of the bottom? Derivative of sum and derivative. Derivative of 1, 0. Derivative of x squared, 2x. So you're like, all right, that's pretty cool. And then don't forget all over the bottom squared, right? And so that's your slope producing machine. Now you could look to simplify, but nothing's really going to cancel out if I go ahead and distribute here, right? And maybe I'm going to argue that maybe you shouldn't look to simplify, because at the end of the day, you don't want this. This is the slope producing machine. This is a formula for all of the slopes. Remember, we want the slope specifically at x equals 1. And if you don't like this dy dx evaluation notation, I can just write y prime of 1. It's the same thing. So I'm going to go ahead and chuck 1 in where I see an x, because it's pretty easy to chuck 1 in, right? So notice the notation. It goes from dy dx to dy dx when I chuck 1 in, right? So this is important. So you're going to get 1 plus 1 squared. That's going to be 2 e to the x, minus 2 times 1 is 2, right? E to the x. And oh, by the way, I don't know why I said x. I'm plugging 1 in for x, right? So I got to erase that, right? I'm plugging 1 in for x. I'm silly. So when I do that, I'm going to get 2 e to the 1, right? And then 2 times 1 is 2 times e to the 1. So I get another 2 e to the 1. So that's actually good news. And then on the bottom, I'm going to get 1 plus 1 squared. So that's 2 squared, which is 4. So up top should be clear, that's 0. So you actually get nervous for a second. You're like, oh no, not 0 over 0. But it's not 0 over 0. It's 0 over 4. So that's fine. 0 over 4 is 0. So the slope of my tangent line is 0, right? So notice the notation here, guys. This is like the bare minimum of what I would expect you to do. So now when I go to write my equation of my tangent line, it's actually going to be pretty nice here. So I'm going to get y minus e over 2 equals 0 times x minus 1. Now, normally we tell you don't simplify, but this one's pretty easy, because 0 times anything is going to be 0. So I end up getting y minus e over 2 equals 0. And if I wanted, although you don't have to, if I add the e over 2 over, I get y equals e over 2. Now, why am I showing you that? Why does this make sense? Well, if your slope is 0, then your tangent line is horizontal. And the equation of a horizontal line is y equals something. So it's no surprise that it's y equals e over 2. So let's just take a peek at the graph here, right? So here's the graph of e to the x over 1 plus x squared. I actually went ahead and plotted the point where we wanted to draw in our tangent line. And when you do it, it looks like there's a horizontal tangent there, right? And the equation of that line is y equals e over 2. All right, so pretty neat stuff there. All right, so let's go back to this now. So what's this all about? This says it says not every function that contains a quotient requires the use of the quotient rule. Sometimes you can rewrite the function in equivalent form. All right, so for example, let's take a look at this guy right here. All right, would you want to use the quotient rule there? Well, I would argue that no chance you'd want to use the quotient rule there, right? I can rewrite this, right? So how do you rewrite this? This is a skill that we've been seeing a lot of lately, right? Break up that numerator over addition or decompose that fraction, however you want to think about it. So I can write this as y equals x squared over 6 plus 3x over 6. This should make sense to you, right? How do you add fractions? If they have the same denominator, you keep the denominator, you add the top. So, oh yeah, these are equivalent. I'm basically doing the reverse of adding fractions. I'm decomposing that fraction. So now I would further argue that maybe I would rather rewrite this as 1/6 x squared plus 1/2 x. Now, why would I want to do that? Well, because this is a sum, and the derivative of a sum is the sum of the derivatives, right? And as each part of this sum, you have a constant times a function. This derivative is going to be pretty easy to get, right? So dy dx is going to be the derivative of 1/6 x squared is going to be 1/6 times 2x to the 1. That's 2/6 or 1/3, right? X to the 1. The derivative of 1/2 x, that's just going to be 1/2. That was pretty easy to take the derivative of that, and I didn't have to use, the quotient rule. Now, doesn't mean if you use the quotient rule, you're going to be wrong. So just for kicks and giggles, let's use the quotient rule here. So let's do it another method. So we'll just do like an OR here. Let's say, all right, dy dx, quotient rule says start where? Bottom. So here we go. Bottom times the derivative of the top. The derivative of the top is 2x plus 3, right? Top's the sum, derivative, sum of the derivatives. Minus the top, wrap it up because it's a binomial there, right? Times the derivative of the bottom. Well, 6 is a constant. The derivative of a constant is 0. All over what you get when you square the bottom. So this is what you'd get. So you're like, all right, so what's the story here? Well, if I distribute the 6, I get 12x plus 18. All of this times 0 is 0, so that's gone. All over 36. So much like I split the numerator up before to simplify, I'm going to do that to my derivative. So I'm going to get 12x over 36 plus 18 over 36. Well, what's 12x over 36? 12 goes into 12 once, 36 3 times. I'm going to get 1/3 x. 18 over 36 is a half, and you can see you get the same thing, right? So these guys are the same. But the deal is, listen, if you can simplify quickly y, then why would you want to use the quotient rule when you can just simplify y first? And that's kind of the thing. Now I want to caution you, don't always look to avoid the quotient rule because that sometimes can get you into trouble as well. But safe to say, if the denominator is a constant, then it's usually a good idea to avoid the quotient rule. All right, so what do we got going on with this one? I didn't leave much work here. I kind of a space I kind of wrote into my work here. So I'm gonna have to erase some of this. All right, so let me erase this. So this guy's very similar. You have a quotient. So if I wanted to take the derivative of that now, I'd have to use the quotient rule. But when you have like polynomials divided by monomials, sometimes it's pretty simple or easy to simplify y first. So that's exactly what I'm going to do. So if I simplify y, right, maybe I'm going to say, all right, up top, I'm going to get negative 9x plus 6x squared. And then on the bottom, all over 7x. So let me again continue to go ahead and split this up. So I'm going to get y equals negative 9x over 7x plus 6x squared over 7x. All right. And all right, so what happens here? So it looks like I can cross these x's out. All right, so we've got little factors there. And I can cross out one of the x's here as well. It doesn't look like an x, but it is. And so then I end up getting, let's see, y equals negative 9/7 plus 6/7 x. All right, so now why is this a good thing? Well, because it's sum. Right? Derivative sum of the derivative. So I can go ahead and say now the derivative is going to be 0 plus 6/7. So it's just going to be 6/7 there. So that's my answer. All right. You can do the same thing. You should try it. You should go ahead and see if you can do the quotient rule on this and see if you get the same thing. That'd be a good little practice, a little, of quotient rule practice and algebra practice. All right, let's do example 4 here. And then there's homework after that. So this will be the last one we do. All right, so it says at what point or points does the graph of x over x squared plus 9 have a horizontal tangent? So this translates to you as, all right, horizontal tangent, that means the slope is 0. That means the derivative is 0. So let me get the derivative and set it equal to 0. So to get the derivative here, I'm going to use the quotient rule. Quotient rule says start in the bottom. So I have the bottom times the derivative of the top, derivative of x is just 1, minus the top times the derivative of the bottom, that's the sum of the derivatives, that's just going to be 2x plus 0, and then all over the bottom squared. All right, so now what can I do? I can spruce this. Watch what's going to happen here. So up top, I have x squared plus 9 minus 2x squared all over x squared plus 9 quantity squared. Now, the reason why I wanted to do that is because these are like terms, I can combine them. And so when I do that, I'm going to get negative x squared plus 9 over x squared plus 9 quantity squared. Okay, so I know it's tempting. Oh, cross these out. These are not like factors. This is not negative parentheses x squared plus 9. This is negative x squared plus 9. So they're not like factors. You can't cross it out. So then what do we do here? Well, remember, we're trying to find when the derivative is 0. So you would show the whole world that, hey, I'm setting the derivative equal to 0. So now how do I do that? Well, the derivative is a fraction, guys. So the only way a fraction can be 0 is if the numerator is 0, right? So I mean, you can write if you want, hey, I'm setting the whole thing equal to 0 like this. You can go ahead and do that, but that boils down to you figuring out when the numerator is 0. And whether you want to add the x squared over and then plus or minus square root both sides, or factor this difference of perfect squares is completely up to you. All right, maybe I'll add the x squared over, and then I have to plus or minus square root, right? Square root principle, and I get two x values here. Two x values that make the numerator 0. Now I really have to check and make sure that they also don't make the denominator 0, because that's not 0 when that happens. That's undefined. But 3 and negative 3 are not making the bottom 0 because I'm squaring them. So that's positive. And then I'm adding 9. So that's positive. And then I'm squaring it. So it's even more positive, right? So even if x was 0, I'm still adding 9. So I'm never going to get 0 in the denominator. So both of these values are good. They'll just make the numerator 0, which means they're two x values where the tangent line is horizontal. So you know what we're about to do, right? We're going to go ahead and graph this bad boy. So if we graph, nope, not that one. All right, if we go ahead and graph this guy, which I went ahead and did for you. So this is the graph of x over x squared plus 9. And then I put the points where x equals 3 is on the graph, right? Take a look. It looks like, yeah, definitely you're going to get horizontal tangents at x equals 3 and x equals negative 3. And that's what we found. Notice my scale here in the y. If you graph this, you might have looked at something like, that, and you couldn't really see it, right? So you kind of have to adjust your scale here where, I shrunk down my y's because the graph didn't go very high up here. And this is 0.2, right? All right, so that's that. So go ahead and give those homework questions a try, and we'll see you soon.